Okay, fine. So thanks, Danielle, for the introduction. Thanks for inviting me. I apologize with the people who have already heard this talk. It's just a few people, but I already gave it. The problem is that once upon a time, our life was easy. Once upon a time, networks were single service, and then they became multi-service over the telephone network. Then they became digital. What is happening today is that we have many technologies for access links, and that over access links, we have a very wide variety of services. What this means is that the behavior of access links has become pretty complex, and design and planning for access links have become difficult. We need accurate models in order to be able to predict what is going to happen with the access links. In particular, in the wireless case, where we need to have careful deployments of technologies, of base stations, and so on. In this talk, I focus on wireless access, but the results can also be transferred to wired just by neglecting mobility. We will consider two types of services. The first one is streaming, which require a fixed data rate for a given duration, which of course is a random variable. And then elastic services that require the transfer of a random amount of data using the rate that the access link can provide. So focusing on a wireless access, as I said, we have many terminals that request access to a base station. I already mentioned streaming services. We can have several classes of streaming services. For example, audio and video, which will be the two different classes that I use in the numerical results. But you can have more. Each class requires a fixed data rate. And if the data rate is not sufficient, the request is dropped. So if the base station is not capable of providing the required data rate, the request is dropped. For elastic services, you can also have an arbitrary number of classes, and they evenly share the data rate, which is not used by stream. Each class requires the transfer of a random amount of data, and you have to fix a maximum amount of simultaneous services. The requests that come in excess of that number are dropped. We have mobility. Users dwell in a cell for a random time. And if a service does not complete before the end of the dwell time, the user leaves, and so the service terminates. Terminates not because of completion, but terminates because of movement. Of course, if you are interested in the case of wired access, then you can take the dwell time to be infinite. So we want to study this with a queuing model. Many terminals, one base station. The collective service request rate is lambda. We assume we can model this as a Poisson process. Not critical because this reflects end user behaviors. The total user plane data rate of the base station is C bits per second. I can split the total arrival rate in a request rate for streaming and the request rate for elastic. So since I have several different classes, the request for streaming is the sum of the request rates for individual classes, and the same for the elastic request rates. I have service which is divided, is different for elastic and streaming. Streaming requests are served according to a multi-service paradigm, whereas elastic requests are served according to a processor sharing paradigm. And on top of this, mobility shortens service times. Access to service is granted by admission control. Admission control may generate losses. Losses are dependent on what is the state of the system. So we have an admission control which is based on state information. For streaming, I cannot do anything except rejecting the request. For elastic, due to the fact that the service is indeed elastic, if I don't have resources, I can just delay the request. The service policy is a Erlang B type for streaming. There is no queuing, and is processor sharing for elastic, where queuing is induced by access control. Now, before I show you some results, let me mention that this paradigm has been investigated before in the literature. And you find in the literature several papers that state that this kind of model is essentially intractable because there is no product form between the behavior of streaming and elastic. The two types of services are dependent on each other. You cannot just solve for streaming and then apply a solution for elastic conditional on the distribution of streaming. Product form does not apply. There is a fairly complex interaction. And so in the literature, what you find are approximations and bounds. This is what exists in the literature. Now, let's start just out of pure curiosity to see what happens with streaming. Here you have the parameters that I'm using for the curves that I'm going to show in a second. I'm taking a total data rate for the base station of 300 megabits per second, which is more or less reasonable. You might have it a little bit higher, but it's kind of standard for base stations. Maybe not the 5G base stations, but for 4G, it's a reasonable number. Data rate video, I'm using 6 megabits per second, which is kind of low. You might argue that we should use something higher. I am aware of this, but you'll see in a minute why I'm being lowish on this number. Average duration of video, 1800 seconds. Data rate voice, 100 kilobits per second. This is on the high side. You might argue, well, you should have used the lower number here. Depends very much, because it depends if you are using a single voice conversation or a multi-party voice call, a Zoom session like the one we have open right now. But this might be considered to be a little bit on the high side. Average duration for voice, 10 minutes. Then elastic file average size, well, this we're going to see later. But is half a megabit. Maximum number of elastic services, 50. Average time in the cell, again, 10 minutes. And then a fraction of elastic arrivals, 80%. So whenever I'm showing you a load, keep in mind that 80% of the requests coming in are elastic. And then the fraction of voice and video arrivals is 10%. Now, let's start with streaming. Let's just look at streaming. But before we do that, consider that there is more than one order or more than two orders of magnitude between the load of a single voice call and the load of a single video stream. If you do the math, you get 7.5 megabytes for one voice session and 1.35 gigabytes for one video. Now, you solve for streaming, which is very, very easy. I mean, this is just a multi-class Erlang B formula. And what you get is strange. Actually, when they first came to me looking these results, they said, come on, that's not possible. That's wrong. But this is what you get. And if you look at what happens for video, you see something which is very familiar. So you see a monotonically increasing loss probability for growing request service. In the horizontal axis, we have the service request per second, and in the vertical axis, we have the blocking probability. What is strange, or what is unusual, or at least maybe it was just unusual for me, but what is, to me was surprising was to see that the voice blocking probability is oscillating. How can it be oscillating like this? And we spent some time trying to figure out why this happens. And this is probably one of the interesting things that we found out. This is happening because of the large difference in resource consumption that you have between video and audio. You see, these are the stationary probability of 46, 47, up to 50 video services. And what you see is that, 50 video services, 50 simultaneous video services consume the entire base station bandwidth. And you never reach 50. Why? Because you just need one active voice connection, not to allow the acceptance of the 50th video. And then you see when the service request per second grows, what happens is that you have these peaks of the probabilities of 49, 48, 47 video calls. And this is exactly what is generating the oscillations, because whenever you are denying access to one video, you are at the same time allowing access to a large number of voice calls. So when one less video comes in, I am allowing 60 more audio calls to come in. And so there is this interplay which generates these bumps and which generates these oscillations. Surprising, at least to me. I'm sure Francois has seen this many times, but this is kind of unexpected. As I said before, the first time people showed me this, saying this is what comes out, I said, no, cannot be. You have a bug. You have a bug in your implementation. You have a bug somewhere. so try to fix it. The guy, after 1 week, told me, no, I'm pretty sure. Okay, then let's write a simulator. And after trying whatever we could try, we finally couldn't escape trying to activate our brains and trying to figure out why this was happening. And these probabilities, I think, are explaining fairly well what is happening in your system. But as I said, up to here is just more or less of a curiosity. The fact that this is generated by the difference between the resource requirement of audio and video is also explained here, because if you keep exactly the same overall occupation for one voice and the video call, and you're just dividing it differently between video and audio, what happens is that if you have a ratio 1 between the occupation, of course, the two curves are exactly the same. If you have a ratio 10, you don't see anything. If you have a ratio 30 or 60, then you start seeing oscillations. This is what happens with ratio 30. This is what happens with ratio 60. And here you understand why I was pointing out before that I am lowish on video and highish on voice, because I am not exaggerating the ratio. So this is something which is likely to happen in practice with the numbers that we are using today for video and audio. But now let's get to elastic. Well, here you have a comparison of the two, of 30 and 60, but let's get to elastic, which is the more interesting part, something that gets us beyond the multi-class Erlang formula. Now, what we found out is that if you apply an appropriate admission control algorithm, then what happens is that you can obtain product form. And what happens is that if your admission control keeps constant the ratio between the elastic arrival rate and the base station capacity, which is not used by streaming, then you get product form. This is something that is just an application of a known result in queuing theory, where you have a combined modulation process and an underlying process which accesses the resources which are modulated by the modulating process. And so what you need is a row for elastic services which has this form, which says that the arrival rate of elastic services depending on the system state, and the system state in our case is the number of active videos, the number of active voice, and the number of elastic. This arrival rate conditional on the state divided by the total out rate of the elastic services, which is a total service rate plus the portion which is related to mobility. If this row is constant, then you obtain product form. And the interesting thing is that if you can neglect this term, which is the term related to mobility, then you also obtain insensitivity. Insensitivity to the duration of streaming services and to the volume of data that has to be transferred through elastic services. Is this so unreasonable to neglect this term? Well, if you are in a mobile environment and you are making a phone call or you are watching a video for a fairly long time, you can expect to experience handovers from one cell to another and so on. If your Elastic service is downloading a web page or sending a WhatsApp message or what are the typical Elastic services that we are using on the internet today, these are fast. So neglecting mobility for this kind of services is not so critical. Which means that with the given admission control, what happens is that you get both product form and insensitivity. So at this point, let's add the elastic traffic. The elastic traffic, again, I have two orders of magnitude in the volume in terms of bytes of elastic traffic with respect to voice. And I already had the two orders of magnitude between voice and video. So there is a big difference. And what do I see? Well, I again see oscillations. Here you have this curve in the inset, which is the blocking probability for video, which is the one we had before. This red curve here, which is the blocking probability for audio, which is the same curve as we saw before. This light blue curve, which is the blocking probability for elastic. Remember, I admit a maximum number of elastic services. This oscillates and oscillates even more than the case of audio. And here you have the residual capacity. What I call residual capacity is the capacity that remains for elastic after I have allocated capacity to streaming, so to both video and audio. And you see that here everything is oscillating. At this point, you might tell me, well, but this is because you used this strange admission control. If you don't use that admission control, but you simply behave normally and let the Poisson flow of elastic requests coming in directly, you don't have all of this. And the answer is no, not true, because here what you see is that here I have three admission controls. One is the admission control that gives product form. Another one is the constant rate. And you see that the constant rate, which is this light blue dashed curve, oscillates even more and even earlier than with my admission control. And then I have an optimal control. The optimal control is actually overlapping the admission control that I showed you. And the optimal control is an admission control that has all information about what has happened up to now and what is happening in the future. So the optimal control is not implementable, is really optimal, but is giving similar performance to the admission control that gives product form. Not exactly the same. Here you see the difference in terms of resource occupancy between the optimal admission control and the constant rate and the admission control that gives product form. Of course, the optimal control is better than anything, because the optimal control is doing the best that is possible up to 7.5. 7.5 is the value of arrival rates that gives 100% utilization for the combination of the different types of services. So that 7.5 is the point where elastic services consume all of the remaining bandwidth after the allocation to streaming. And of course, at that point, you jump to the maximum number of possible elastic surfaces. So that is more or less the story, and this just is a summary, and the interaction, provided you have these big differences in volume of megabytes used by video, audio, and elastic, you see these oscillations. You see these oscillations both on the smaller class of streaming and on elastic. The interesting part is that with an appropriate emission control, you can get both product form and insensitivity. And that's the end of the story. I might perhaps add that one thing that is normally asked by the audience is, well, yes, but in reality, the streaming are not fixed data rate. If you are watching a video, you clearly see on your screen that the video jumps in quality, because depending on how much resources you have available in your base station, in your access link, in your whatever, your quality jumps up and down, which is probably the biggest limitation that we have in this analysis. We are working on it. I don't have results yet. We probably have one way of accounting also for this, but next year maybe. So thank you very much. I'm happy to take questions, but before questions, first of all, if you want some details, there is a paper that has just been published at WOMOM 2 weeks ago. So if you go there, you can get it. If you don't have access, drop me an email and I'll send you the paper. Second thing, allow me a short advertisement. We have a beautiful conference in Torino in September with the best keynote speakers in the world. Francois is one. So please come to Torino, please come to quasi-optimal. We are going to make a very enjoyable conference. And in case Patrick knows, one of the other keynote speakers is Janine. So we really have the top guys in the world in networking giving keynotes at quasi-optimal. So please come. But please also come to ICC in Rome. You probably received 10 minutes ago a call for papers in your inbox. The first call for paper was sent by IEEE today. I think by chance. I don't expect them to know that I was advertising for ICC here. But please consider ICC, please come to Rome. Okay, questions.
Questions? Yes, you are looking to communication to coding rate. So if you think of the requirements of the base station would be very different depending on the geometry you're using. You are all at the edge of the cell, it will be more demanding in terms of consumption of resources. So can one include this type of geometry constraints or fluctuations in the mobile world?
Well,
Marco, Could you please repeat the questions? It's impossible to understand anything from the audience.
Yes, yes. So Francois was saying that the resource consumption will depend on the position of users in the cell, which is quite correct in the sense that if a user is at the cell border, is going to use a less efficient coding and modulation scheme, which means that the amount of slots that he's using is larger. So it is like spending more of the base station resources in order to provide the same quality to a user which is at the border with respect to a user who is close to the base station. Now I can have, there are two answers to this. The simple answer is I can have many different classes of streaming. So I could have streaming for users which are close, streaming for users who are at the cell border. So this is very easy. What is more difficult is accounting for variations. As I said before, variations that are depending, why is this difficult? This is difficult because in our queuing models, we have a customer that comes in and requests a given amount of resources. And then another one comes in, it might have a different request, but the one which is in service normally does not change his consumption of the service in the queue. So having different classes to describe users which are in a good position or a bad position is easy. What is more difficult is changing during service within one cell the amount of resources that is given to it. We are thinking of a way to accommodate the fact that there is a dependence on how many resources you have available. What you are saying is that there could be a dependence which is not related to how many resources are available at the base station, but there might be an exogenous dependence. That I don't know. Might be possible, but I don't know.
Yeah, so the question is, I have on the oscillation. Often some randomness might dampen the oscillation.
Yes, Francois is saying that this variability might dampen the oscillations. Well, let me say that I was scared after accepting these oscillations, which took a while. I was scared by the fact that these oscillations were due to the fact that there is a multiple, an integer multiple between the capacity required by one video and the capacity of the base station. So we try to modify that. So if you have 300 and instead of having 6 megabits per second, you have 7, doesn't matter, the oscillations stay. And then I was scared of the fact that, well, but if you reserve some capacity for voice, the oscillations will disappear. And the answer is no, the oscillations remain, even if you have some reserved capacity for voice, which is very natural because the reserved capacity you consume, and then when you are stuck at the end, you are stuck at the end. So the oscillation phenomenon appears to be rather persistent. Then I don't know. of course, there are many dimensions to explore.
Other questions? Now, 2 points of clarification. On slide 22, you have 0.8 and 0.1.
Mm-hmm.
What happens to the resting 0.1?
Oh no, 0.1 is for voice and 0.1 is for video.
Yes.
So it's 0.8, 0.1, 0.1. 0.8 elastic, 0.1 voice, and 0.1 video.
So that makes 0.8 is 0.9 total.
No,
No.
it's 0.8 for elastic,
Okay.
plus 0.1 video makes 0.9, plus 0.1 voice and makes 1.
And then what is the admission control you have? Is it zero time admission control? It doesn't need any time to decide whom to admit or whom not to admit in the queue?
No, it's instantaneous, no delay.
Are there any distant questions? I will have one more question, Marco, if I can. We are having more and more intelligence in the edge, right? The mobile, the edge, multi-axis edge computing. And those nodes have the possibility today to say, okay, I know there is a buffer for the streaming. When the voice is coming, for example, or when a web page is being transcribing, I can stop or delay the streaming a little bit, because anyhow there is a buffer, and the end user will be insensitive to all these things. So this is just a very simplistic example, but by introducing some intelligence in the edge nodes, in the edge of the network, sorry, you may admit more traffic, because you have information about the relevance of each of the individual flows, right?
Mm-hmm.
And this will change maybe the results. The fact that once you admitted the flow, the way there are multiplexes will depend on the type of flow. And the edge will have this intelligence.
Yes, but this is more or less what I'm doing here with that weight that I'm keeping outside. And keep in mind that once the elastic service is admitted, its data rate can go to 0, because if the base station data rate is consumed by the streaming, then you essentially are pausing the elastic.
But I'm saying the contrary. To pause the streaming.
To pause the streaming.
Because I have a buffer for the streaming in the destination. This is what
Yeah.
today.
Yeah.
And this is available in some devices already. So by doing so, we are changing the dynamics. And it seems that you will be able to admit more traffic.
Yes, probably. Yeah.
And I don't know if this is affecting or not the oscillations you are describing.
That I really don't know.
And the second question I would have is, where do you see this access control to be implemented for the elastic traffic? In which part of the network? Because it's not really the case today, right? That we do implement the admission control for this type of traffic. You may have admission control for the streaming traffic in the service platform itself, but for the elastic traffic, how do you see it?
Well, I mean, you are anyhow requesting service to the base station. So in the moment you are requesting service to the base station can delay an answer, and so can essentially make you wait.
Right. Thank you.
Okay.
Any other questions? No?